So that was Richard, and now we have our next invited speaker. She's Dr. Alessandra Sciutti, and she's from the Italian Institute of Technology. And her research focuses on the investigation of the role of sensory and motor mechanisms in human-human and human-robot interactions. And her topic for today is more humane learning. It sounds very interesting. Over to you, Alessandra.
Hi, thank you. Thank you for having me. Can you see my screen?
Yes, we can see it.
Okay, very well. So thank you for having me. And today, indeed, I want to touch upon a topic that came out already multiple times. So the fact that something that is literally a child's play for us, so learning from others and learning how to interact with others is such a difficult thing for machines. I work with robotics, but in general for intelligent machines, this is super, super difficult. And why is it so? So I think that some reasons have been nicely highlighted by Dana Coolidge in her keynote at the ICDL a few days ago. So learning is particularly difficult in situations like those of normal interaction, both among humans and with human and robots, where you can't actually fully simulate and properly simulate the partner, because it's so difficult. We've seen it today already, modeling completely a human partner, where you cannot really make a lot of mistakes to learn because errors are costly. And if you imagine an interaction, indeed, making mistakes can really break not only things, but really also the bond, the rapport with the other person. And when, of course, time matters a lot. So you can't imagine of interacting, millions times to have to acquire a competence. So patience came out also in the previous session very much. So, and this, according to me, clarify very well properties that are crucial for HRI and for human-machine interaction in general. And plus, I would add another source of problem that is really crucial when we are trying to interact with each other and learn from each other. So the point is that when we are interacting with a machine, we are not sharing the same word, even though maybe we are physically interacting with the same environment. Why is it so? Well, the point is that we as humans are not merely perceiving what is in front of our eyes. So if we imagine of also disregarding the difference in sensors, if you want. So let's imagine having the robots who has very, very human-like sensors. So the cameras work exactly like our retinas, etc. Well, that would be not enough yet to really capture what human perception is. This is because it's as if our brain continuously modifies, shapes what we perceive. We have a sort of anthropomorphic filters that transforms reality for us. So we, of course, realize that only sometimes. So, for instance, when we are faced with visual illusion, we realize that our brain is filling gaps. So it's giving us much more information than what physically is in front of our eyes. But this is particularly central in the context of interaction, because it modifies completely the way we perceive others' actions. So this has become clear also from neuroscientific studies. We have really circuits, parts of our brain that are responding both when we are performing an action and when we are seeing someone else performing an action. This means that we have a sort of our internal vocabulary based on our previous experience that allows us to see not just a movement, but the goal behind the movement, the intention behind the movement. Sometimes even something more, the attitude with which that particular movement is performed. This means that where a machine sees maybe precisely velocity properties, acceleration properties, and apparent motion, we see a goal, we understand a state, we infer so much more with no conscious effort. So we are really saying two different words. And to us, it's so easy because we have it almost for granted since the very earliest moments of our life. So even newborns know where to look in an interaction to get what matters. They can recognize biological motion. They can direct their attention to other people's gaze. They can, they actually preferentially orient to faces. So since our earliest days, we are really designed to interpret the word, to catch from the word what really matters, to favor interaction, to help us deal with that. And so the challenge is, can we provide the same kind of richer, augmented perception to robots, to machines? So this means being able to, on the one hand, knowing where to look at when we are interacting with someone, to really gather the meaningful feedback to adjust our behavior if we are a robot. And on the other hand, it means to select among the immense number of actions that we can perform, the right ones that can really be legible, understandable, intuitive to the eyes of our partner. And to make it a little bit clear, I want to give you a few examples. So for instance, we can try and make the robot read facial expressions. So understand how the face is changing and as a function of a machine behavior. But why is it so? Well, because this can inform us if what we are learning and the way we are behaving toward a human is correct, and adapt. So let's consider the example of a very good physical therapist. If we are trying with our robot to be the same and learn the best policy to train our patients to recover its abilities, well, the first impression, the first idea could be that we will try to maximize the performance in performing the training task. But then we would totally lose a very other important component. Is the person frustrated? Is the person losing engagement? So knowing where to look at in an interaction can really shape completely the way the robot learns, because it will rely on different meaningful information. And this applies, of course, to the context of training, rehabilitation. It can apply in general to personalization. So reading from the environment, reading from the reaction of participants, what they prefer to do, and then learn progressively to modify the robot behavior and personalize to the desires and preference of each. But of course, there's no only facial expression. Gaze is so important since early childhood. We have seen, well, it's super important also for machines. It can be a way to understand what to do next without the need for listening or understanding language, or even the need of reading pointing actions. It can be useful to understand whether the person is actually reliable, to build a sort of model of trust within the robot. So to understand whether the person in front of us is lying, just by modulating or monitoring actually modulation in the pupil dilation. And it can be also used to support the robot to learn by itself. So Jonas Gonzalez, this is a part that I extracted directly from his PhD thesis recently passed. He's proposing the importance for robots to actually exploit their own experience with the world, with their body also, to get to understand better the environment and to rely on existing regularities that characterize humans' behavior to provide a sort of information to allow for learning. So he originally developed a system to allow the robot, our iCub, which is a robot baby, to learn to localize speakers in a room. And it has been just presented at ICDL this year, so you can still find the beautiful link to his video on the program webpage of the conference. But more interestingly, he's going on now asking, well, what if there is not just one person who speaks? And that's very common. And so he proposed an idea of having to look at regularities, like when there are two people speaking, and maybe you can find out who is the one by looking for correlation between the movement and the changes, the visual changes of the area of the mouth and the envelope of the sounds, and then using this information about the correlation as a guiding signal to really allow the robot to progressively learn to recognize the active speaker. And in principle, the system seems to work. Of course, this, for the sake of time, is just a subset of example of important points to focus our attention on, and with our, I mean, of our robots, of our machines, when we are looking around for feedbacks that could serve for the robot to really actually learn how to react, how to change, how to behave in relationship with the person. But as I mentioned before, this is only half of the story, because the other half of the story is really knowing what we as humans perceive, what we notice in someone else's behavior, to create my behavior, to generate behaviors that are really intrinsically or intuitively legible to the eyes of the human partner. This is clearly particularly crucial for robots, where you can really manipulate and operate on the way they move. And this is something that we have explored recently with Marco Matarese master thesis, where we asked whether using the behavior of the robot, so we could make a little more clear, more transparent to the eyes of the human teacher, how the learning of the robot was going. So the task was quite simple, because we needed an HARL task that could be short enough in time and feasible enough in terms of no breaking of the robot to be done in real human-robot interaction. And it was like teaching to the robot a sequence of color that he had to point by pointing to balls on the table, as you are seeing in the video. And the human teacher was giving feedback to a joystick, like positive or negative feedback, as a function of whether the sequence was correct or not. And our idea is, okay, how can we inform in a natural way of the state of the learning, the human teacher? And drawing inspiration from the theory of emotion by Brockens and Sciutti, we imagined of trying to be super communicative by modulating both the robot behavior, so the kinematics and the coordination by eye and arm, and the facial expression as a function of the temporal difference error. So the robot could show like a very uncertain or a very uncertain movement, both with the eyes and the arm, and could also show a happy or a very sad face as a function of how, let's say, confident it was of the previously selected action. And we compared that with a, let's say, baseline mechanical configuration in which the robot was just doing its deeds. So it was just pointing to the balls without these additional sources of information. What we found that when asked through a lot of questionnaire, we asked participants what they thought about this, two different approaches, and they liked much more what we call the human-like. They appreciated it. They ascribed the more experience abilities to the robot, etc., etc. But if we look at how the actual interaction went on, we realized that not all communication channels were equally effective. So the uncertainty, for instance, expressed through the motion creates some problems and some delays and misunderstandings in the human teacher that couldn't understand why the robot was not directly reaching for a particular ball. And the facial expression also were appreciated, but people were expecting them to be a response to their feedback, not to the internal state of the robot. And this tells us that it's not so easy to really convey also through rich and human-like behavior the internal state of the robot. And of course, also in this case, just for the sake of time, I'm not touching all the different features that you can imagine of modulate to really transferring and making the interaction and the robot behavior much more readable to the eyes of the partner. And I slightly touched the topic of transparency, very slightly, but I didn't talk of trust, because I would like to present to you a study on trust in which the robot was not learning at all. So it is a non-learning kind of task, but it really was eye-opening for me to understand how complex is to understand the trust toward machines when they are put in interaction, even game-like interaction with humans. So we conducted a game. It was really a treasure hunt. We hid some objects in a room, and the robot could be asked for hints. People were searching for the objects for a limited time. If they found them all, they earn a reward. And then at the end, the robots tried to convince them to gamble the reward and to find that another hidden object at the risk of losing everything. We found this is a big, let's say, an image of how it went by. So people had different strategies. They asked for hints. But what we observed is that during the 30 minutes of game, already people showed a very strong increase in their trust-related behaviors toward robots. They complied a lot with the suggestion. And at the end, all of them, or those who won at least, decided to gamble according to the suggestion of the robot. So this got us to understand that indeed it is possible to create a sort of trusting-like behavior in a game-like interaction with the robot, even after a relatively short time. But then we ask ourselves, okay, in this case, the robot was reliable, but what if it breaks? And therefore, we created a lot of different interesting failures of the robot. I show you just one, and there will be a noise, I warn you. So I hope you can. So there was even a moment in which the robot, during the game, without no warning, crashed. And we took quite some time to ensure that the failures were critical, at least to our judgment and the judgment of a validation study conducted online. So we asked, do you think these are terrible failures to happen? And a lot of people said, yes, my trust would decrease if I were to interact with a failure like that. These trusts are quite obstructive, etc., etc. Then we conducted a real experiment in which the robot did the same treasure hunt with these failures, and we considered two conditions. One in which the robot just failed, and the other, which we call transparent. We added a little explanation after each failure. So the robot was saying, my control boards have some problems, or something like that, to provide a reason why this strange happening occurred. And of course, we had two very simple hypotheses. Okay, failures will lead to lower trust, and transparency will mitigate this loss. So we will have a higher trust. So we ran the experiment. Again, another little video excerpt, so where the robot crashes, someone cares, someone don't care, someone don't realize it's happening. And these are the results. So the first result is, of course, that performance is lower in the game when we have failures, even though this might depend also on difference between the groups of people that we tested. But the interesting finding that for us was quite unexpected is that transparency, this kind of transparency, resulted detrimental. So people performed less nicely when the robot was providing this little explanation after the game, and asked less frequently hints to the robot. And it was perceived much worse also. So if you notice, when we asked about pre and post to judge, like the anthropomorphism and the animacy of the robot, in the transparent condition, they decrease significantly. And also, if we look at the other valuation of the robot, they decrease significantly in the transparent condition with respect to the one in which there was no utterance by the robot about what happened. The only positive things is that the workload measured as the nasal TLX questionnaire decreased as well. So it was unexpected. Transparency didn't help at all, apparently. And we didn't find the reduction in trust that we expected. So if we compare the responses that we had in the real game about game obstruction provided by failure or robot trust, in the real game, they were totally different from our online survey before. So people didn't care about the failure, and this did not interfere with the trust. So our take home was that it is very difficult to actually predict and model how the unfolding of trust by humans toward machines, even if we make a very strong reasonable assumption about what should work in terms of favoring an increase of trust. So to some sort of sum up what I want to say, okay, we realize that learning, especially in social contexts, is so complex, there are so many difficulties. What can we do? Well, my suggestion in this direction is, first of all, as far as you can, try to test the systems in real life, in real interaction, and maybe sometimes a humanoid robot can help because it allows you to have an agent that you fully control, but at the same time can really entertain physical and interactions with human partners. But what if you can't? Well, then maybe it's the case to create simulation environments that really allow for nudging and really investigating the social components of interaction. And for that, for instance, we created, actually, this is Pablo Barros' brainchild, the Chef's Hat card game. It is a card game, first of all, so a real card game inspired by pizza making. So Pablo lives now in Italy, and that's quite clear, and which is super entertaining on the one hand, and sufficiently complex to evoke a lot of social interactions when you're playing with your friends. It also designed so that it is relatively easy to port it in artificial scenarios. And indeed, Pablo developed a simulation environment where agents can play the Chef's Hat card game, but not only, also an online version where agents and humans can play together. So really exploring the richness of this kind of interaction. As I mentioned, it's a sufficiently complex task indeed to learn to be a chef for an agent, but it is possible for reinforcement learning agents to learn and adapt to be competitive in this card games. And you can also play a lot on that. You can create agents that support continual and online learning. You can imagine of creating to play along also with contrastive reinforcement learning. And as an evidence of that, we can say that there are already 32 types of different players, and that it is open for more. It's really a gym, if you want, to exercise on this kind of interaction. It just ended a few months, last month actually, big challenge with the Chef's Hat, where this was really used to run a tournament among different agents to compare their abilities. And this could also become a nice test bed to explore some elements that could be crucial for inputting, let's say, social components within reinforcement learning. So first of all, we explore the possibility to explain competitivity within this setting by, but I don't enter into details because I'm seeing that I'm running late of time, but you can see that on the paper. But let's say transforming confidence into a sort of a mood, so something more continuous and slightly more explainable also to a human player. And we are more recently trying to also introduce concepts like rivalry. So sometimes for us humans, when we play, we don't care so much of winning in general, but we want to win against this special enemy, the special rival that we have. And this is very common. And so we try to introduce a sort of human-centered metric that was based on rivalry to compose the reward function of our agents. And we have already done a preliminary test, and we found out that indeed human participants perceive different rivalry levels within our agents, and this can really modulate human responses. So to conclude, this is just a sort of advertisement. So please use the system and contact us, especially Pablo, if you want to, and if you think that this could be useful for you. This, I think, are like humane machines. In particular, I speak of more humane robots, but this applies in general. So robots that are more considerate of us as humans and learn to see the world through our eyes. With that said, I just want to thank you for your attention and thank all the incredible people whose work I just briefly showcased today and all the others. Thank you very much.
Thanks, Alessandra. That was a really interesting talk, I have to say. I was just wondering, this kind of learning from nonverbal cues, how would it adapt to situations where you have someone who does not have like the standard way of showing these nonverbal cues? For example, say some children with physical or mental disabilities, would it be able to adapt to their way of communicating these things?
That's a very central question, and then indeed it's a very active field of research, that of let's say personalizing the reading and the behaving to the individual needs. So what we do in this direction is that we start from let's say basic findings from neuroscience that are generally applicable and usually do not depend, for instance, on cultural difference. We are really going low level. So, oculomanual coordination. So mechanisms that are not top-down modified, they are really bottom-up. And by using that, this allows us to have a sort of generality in what we propose. But of course, in the case of patients or in the case of social disorders, this might not be enough. And that's where indeed the entire issue of learning from your partner really comes into play.
Right. I suppose this kind of approach could also be applied in cases where there is a significant difference in the way of communication through because of cultural aspects.
Well, in this case, this requires an ad hoc, if you want, learning. We are now exploring, for instance, the understanding of gesture, the Italian gesture, very particular, very complex meaning. And this is, of course, on top. I do believe that you need somehow to acquire first or have a baseline that represents like the core regularities of motor control that are sort of universally understood by the humans population. But when you really want to deploy a machine into an environment, you first need to adapt to your individual partner and then to the cultural needs of that particular milieu. And that's really what is so challenging, especially for long-term deployment of robots in society.
Right. And I just one last question is, so I assume is this like very data hungry in the sense that you need to have a lot of very diverse data to learn from? And if so, is there any publicly available resource that everyone can use to do these kinds of works?
Well, you touched a very painful element. So exactly the data hunger is really one of the reasons why we cannot, especially working in HRI, leverage on what has been developed in AI and just take it and put it on our robot. Because while robots move, they behave a lot. The adaptability to different situations is really something that we cannot achieve by, taking a data set and porting it on the robot and we are done. So there is a lot of work exactly on self-supervised learning, on transfer learning of different types of continual learning, really designed with the idea of limiting this data hunger as much as possible, and leverage on the possibility of acquiring a lot of data without the need of a manual supervision of a human.